Recording in progress.
Okay. We have a 10-3 and 10-4 today. Do not have an activity, so we're just gonna do our thing. So I suppose we could always do, yes, last week's activity. We are continuing with the hypothesis testing. So 10-3 and 10-4 do different types. 10-3 is for means. 10-4 was for standard deviation. I had to check. So honestly, I was looking through the notes, like the PowerPoints they gave. They made a really nice table, and I think will help us. So I'm going to give you the table. Whoops, I'm not writing pink yet. 10.3, this is hypothesis. Testing. Population. Okay, so how do I want to do this? H0. Then we have two-tailed. Then a left-tailed. And a right-tailed. And then I will draw the picture for this. And that is more far than I need. Okay, that is way more space than I'm gonna need for what I'm about to write. I got a little, yeah. So our first one is mu equals, as a note, this was our and I swapped what I'm writing, make sure I have this right. This was our population because we want to be here. Equals test / sample. Yeah. Okay. We have mu and mu naught. It's sometimes hard to tell like which looks the same. So for all of these are null hypothesis, meaning there's no difference. It's mu equals mu naught. And that's going to be going forward for any of our tests. So if it's standard deviation, it's mean, it's proportion, it's our sample is the same as our population. There's no difference. Nothing's going on. For our alternative hypothesis, which is our H1, for a two-tailed test, we just say it doesn't equal. I'm going to throw this down here so I can draw some pictures with it. All right, for this one says our test is less than our actual, and this, or our population rather, and this one says our test is bigger than our population. So all of these were set up to where we make our mean 0 usually. We adjust it to be 0. So for our two-tailed test, we're saying that our test value is in the tails. So it's different. It's not bigger, it's not less. Well, we're going to see if it's bigger or less, but just that it's different. We're not going to claim one direction or another. For a left-tailed test, we have a bigger area. So say our alpha levels are always the same. So alpha whatever. So in this case, we have alpha half over here, alpha half over here. This one, alpha. We have our full alpha on the left. So our significance level. So more space over there. And we're saying our test value is going to be bigger. So it's on the left for our alternative hypothesis. And this is the same picture, but flipped. You know, assuming I could draw symmetrically, which we all know I cannot. Look how cheap. Here is my full alpha, and we want our test. So this is all H1 for each of these cases. So if we're in those tails, so those the shaded region, we would say there's a significant difference. We would reject the null hypothesis. Because there is a difference. Our test value is far enough away from our population value that something's going on. So I always talk about these in terms of experiments because my original background was psychology and we did a lot of psychology experiments. So basically says our control was our population and our alternative is our test group. So we want our test group to be different than our control group. So I realize for these, it's population versus our little subgroup. And I say that differently, and that's why. It's just from my background, that's how I learned these. And it's hard to kind of switch that. Okay. Oh, can I scroll past that? Are we good? I don't want to, fly. So for our means, our test statistic, we've used this before, is X bar minus our mu naught all over S over root N. So our X bar is our sample mean. It's the one for our little group we're looking at that we found. Our mu 0, mu naught, is our population mean. And that's what it was when we did some of our tests earlier. So we don't need to worry about that. Like it doesn't change. S is our sample standard deviation. And N is the number in our sample. That's the number we're looking at for our particular sample. And the degrees of freedom is going to be N minus 1. We need that to look up our critical values on the table. Yeah, and if we do the P method, the p-value method, we will also need our degrees of freedom. It's just 1 minus the number in our sample. If our degrees of freedom isn't on the table, we choose the closest one we have. Because for these, they only have the small cases. Anything bigger, I think they go like by tens or something. We'll see that in a sec. For our criticals, so looking up. So table 7 in the appendix of the book. So if you go on to Pearson, the e-text, you can follow the links to get there. When we did the stuff last time with our z-scores, I could give you the critical values that we use most often. Because we have a degrees of freedom that depends on the problem, I can't give you those for these. You have to look them up, which is a bummer, but whatever, we'll make it work. Things to note for a two-tailed test. I think we're going to use these. We look up, sorry, my handwriting is worse today. Plus or minus T alpha over 2. So that's our picture up here. The little bars, that would be our T alpha over 2, those numbers we look up. A left-tailed. We look up and use negative T, whatever we look up, left. And then a right-tailed. We use the positive of whatever we look up. And then for your T value, or excuse me, P value. Yeah. Find T, sorry, look up. So look up your T value on the chart, compare that to your alpha or alpha over 2. You want it to be farther from the mean than either of those. So depending on your tail, it could be positive or negative. You just want it to be farther away than the those values would be. So either method we use, we're going to have to look up a T value of some sort. So either the critical or the T we find. So for our crit or our classical method, what we're going to do is we calculate T, and then we compare it to our T crit, whatever that is. So we're comparing T's for our classical method. For our p-value method, we're going to calculate T. And look it up. And then, which this is going to give us our P, and we compare. P to our alpha. So for both methods, you're looking up a T of some variety. On the classical, you look up your T critical, you figure out what that is. On your other method, you're going to look up the T value you find and find a P value. So classical, you're comparing T's. P value, you're comparing P's. It just depends on what we're doing. Okay. Let's find an example of this guy. Is it here? Yeah. Is this my slide? Slide 100. Okay. We have the mean heights of American males as 176.3 centimeters. So that would be our mu naught. And we have some presidents, and they have a mean height of 180.1 centimeters with a standard deviation of 7.1. I will get this all written down when we go back. So we're going to treat the presidents as a simple random sample and determine, are they taller than the average human? So do we elect taller people as president? So, and we're looking at the 0.05 significance level because, again, if we're wrong, who cares? It's going to mean all of nothing to us if we're wrong. So it helps to compare. All right. So our population standard deviation, or not standard deviation, that is the next section. Population mean was 176.3 centimeters. Our sample mean is, where did I? 180.1 centimeters. The standard deviation they give us was 7.1. And then our degrees of freedom equals 43, which means our N. Oh, alpha level. Alpha is 0.05. Okay, we get to do the hypothesis testing, etc. So, null hypothesis is usually the straightforward one, comparatively. This means we're going to find the mean for our sample here isn't any different. We're not going to find a significant difference. So our mean is just going to be 176.3. Our alternative hypothesis, well, it was written, it says that they think presidents in general are taller than the average human male or American male, whatever. So in this case, that says to me it's a one-tailed test. So we think our mu is going to be bigger than 176.3 centimeters. So we're a right-tailed test. We want to find bigger. Wherever our t-crit value is, or our p-value, is either going to be t-crit or our alpha level, depending on what method we look up. So if we're in that tail, we have a significant difference. If we're to the left of it, we don't. All of that on the screen at once. Can I manage this? I never planned to give myself enough space. Okay. So how we're going to calculate our statistic, we have to do this regardless. So the t that we're measuring, our formula is x bar minus mu 0 all over s over root n. And this is a calculator problem. Okay, so for this one, my X bar is 180. $180.1 minus 176.3 all over my standard deviation, which is somewhere on there, 7.1 over 44. Okay, do this in a couple steps. I recommend playing along. So, because this one's a little trickier to calculate just because of the double division. So my numerator gives me 3.8. My denominator, I'm going to say 71 or 7.1 divided by that. So my calculator gives me more decimals. I'm just going to put dot, dot, dot and leave it there to not worry about it. Then I get 3.8 divided by that monster number. This gives me 3.550. While I'm at my chart, I'm going to look up my p-value and my t-crit at the same time. You really only ever have to do one of these, but we're going to compare them at the end. So that is the wrong screen. Oh, good. I don't have this. Okay. The area in the right-tailed, since it's a right-tailed test, we just have 0.05. So I'm going to be looking in this column here. Can you see where my little hand is? So just to the left of where it says area. And our degrees of freedom was 43. I don't think our chart goes down quite that far. We go straight to 40. So I'm going to use 40. My t-crit is, what column am I on? This is easier on a bigger screen. I'm on this column here. Can't see where my finger is, but crap. Okay, so my number, my critical value is 1.684. All right, we'll come back and do the p-value method in a sec. Too much at once. This is my critical value, and we treat this as our 0. If our test statistic is bigger than our critical value in this case, we have a significant difference. If it's not, we don't. So our test statistic is 3.550. Where does it go? Does it go to the left of our crit or to the right? Is it bigger than 1.68 or smaller? So our test statistic, our 3.55, is that to the right of our t-crit, which is that 1.68, or is it to the left of that? Based on like our, yeah, it's to the right because it's bigger than, yeah, then it's our general number line. So the right side's bigger, left side's smaller. So we're gonna be, say, here-ish. That is our calculated t. Based on this, Do we reject the null hypothesis or fail to reject it? So our null hypothesis says that our group of presidents does not have a different height than a group of other people. But we find that we do have a significant difference. So when that happens,
This one I get confused on all.
so if our test stat is significant, we reject. So since our test, say again?
Rejected.
We reject the null. And don't even think about the alternative. That's just to help us draw the picture. Look at the null.
The null, okay. I always look at the alternative, but
I-
that's my preference.
I want to as well, so I feel the pain on that, but no, go back to, because that's what we care about, not the null, but we either reject the null or fail to reject.
Okay.
So we're gonna say since our stat is bigger than our critical value, we reject the null hypothesis. I'll actually write that out. Since E equals 3.55. Secret. One important note, so we can't necessarily use the same exact formula like the pink board's written there. It's written in this way because it's a right-tailed test. We want our number to be bigger. If it were a left-tailed test, we would have to be smaller to have a significant thing. We just have to be in the tails. So we care about the tails. We're in the tails. Great. We reject the null hypothesis. There is a difference. Found a significant difference, we reject. And these are tricky, like calculating the stuff is relatively easy. It's how do you put this in stats language? Because it's counterintuitive. It's backwards as to how you want it to be. Rejecting is what we want. Usually you don't want to reject things because that's bad. No, in stats world, rejecting is the yay. We do that. Okay. We're gonna do the same thing, but now we're gonna use our test value or p-value method. It's a one-tailed test, so we just use our regular alpha. And our test value, 3.55. So we're going to see if we can find our p-value based on this. In this case, we're going to read our chart backwards. Oh, there we go. So we're in the 0.05, which is this, what column is that? 1, 2, 3, 4. It's the fifth column. So look down this fifth column and see if we can find something close. Oh, no, sorry, we don't have to look at that column. We're just looking for 3.55. Where are you? There we go. That one's pretty good. So I got 3.52. I don't think we're going to be able to improve that. So what is that p-value? 0.001. So the t we found, we look for it in our chart or as close as we can get without going over. Our degrees of freedom is in the 40s. So yeah, 0.001. We want our P to be smaller than our alpha. If P is smaller than alpha, we reject the null. Because it's small enough. So our P was 0.0001. Our alpha was 0.05. So we're happy. We reject the null hypothesis because our p-value is less than our alpha. We're good. We reject and we're done. So apparently the presidents are taller than the average person. Who knew? Actually, that's a saying that if you look at whoever's usually it's two candidates for president, the taller of the two tends to be the winner. I find that interesting. Just some little factoid. Doesn't always happen, but. Okay. Oh, did I have results for this one? 103. Okay, here's their picture of it. So they plotted our t-crit and they said, oh, hey, our test statistic is to the right of it. Great, that's what we want. They draw better pictures than I do. Okay. Oh, I should have brought candy bars, but I didn't think about that. We have fun size Snickers bars are supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so the mean weight is 20.1 grams. We have quality control, is concerned about this, takes a random sample of 11 candy bars and weighs them. So we want to look at our data values here and find is our average, our mean weight, is that bigger than the 20 grams or smaller? So we have a 0.01 significance. We don't care if it's bigger, we care if it's smaller. So this says to me, it's a left-tailed test. So so what I wrote. Oh, no, not equal, sorry. I was looking at my stuff here. They claim our mean is 20.1, and the rest of this we're going to have to calculate ourselves. So our null hypothesis says there is no difference. We're going to find our mean is 20.1 or close enough. Alternative hypothesis, we just says it's not equal. Because if our candy bars are significantly underweight, that's a problem. We'll get fined and have to, pay more. If they're overweight, we're giving away more candy for free, which is apparently a bad thing to them. So we want to be as close to our at weight as possible. All right. This one. So here's our data values. Can I zoom in a little bit? I will give you the standard deviation, but you find the mean. So we have, 11 data values there? Find the mean of those. Because you could do that one on your phone if you need to. Standard deviation's a little trickier. Video while we do that.